Okay, great. So we continue the second day of the workshop with Yuri Leskovets from Stanford. Please, the floor is yours.
Thank you. Thank you for the invitation to this workshop. I have actually decided to present some, I would say, interesting empirical work that tries to connect network science with neural networks. And this is joint work with a student in my group, Joshua, as well as our collaborators at Facebook AI Research, Kai Ming and Xiang. Here is how we think about this, right? So neural networks are essentially graphs, right? Neural networks consist of neurons, and there are connections between neurons, and the structure of this underlying neural network affects the predictive performance of the neural network on a given task. So what we wanna do is to study whether there is a link between the graph structure of the neural network and its underlying predictive performance. And if there is such a link, then the question becomes, what are kind of the structural signatures of well-performing neural networks, right? And can these signatures be generalized across different tasks and data sets? So in a sense, what the goal of this work will be is to apply tools of network science to study the structure of artificial neural networks and try to gain some consistent connection between the structure of the neural network and its performance, right? So the main question we want to ask is there a connection between the neural network architecture and its predictive performance? And this is a paper we published at ICML this year titled Graph Structure of Neural Networks, and it's available on arXiv and everywhere and on our homepages. So as I said, what we want to do is we want to build a bridge between the neural network architectures depicted here on the left, as well as with the network science. So basically the study of characterization of real world networks, and see if we can kind of connect the two fields together and start analyzing what are the neural networks that perform well, under what conditions do they perform well, how many computational operations do we need to be able to do good predictions, and so on. So our work will have three steps. First, we need to ask, how are we going to represent the neural network as a graph? And our main innovation here is that we don't represent the neural network as this graph of layers of neurons, but we have actually developed a novel representation of neural networks that we call relational graphs. Then I will show that basically there is a bijection between the traditional layer by layer representation of neural networks and computational graphs and the relational graphs. So it means that the relational graphs can represent diverse neural network architectures, right? I can take a multi-layer perceptron and represent it as a relational graph, or I can take a deep convolutional neural network, maybe a ResNet or a VGG model, and represent it as a relational graph. And now that we have a way to represent the structure of neural networks using these relational graphs, we are going to empirically study the structure and the performance of the underlying predictive model. And what is interesting and what kind of the high level finding will be is that these neural network architectures that are performing well are surprisingly alike. And they are kind of independent of the underlying realization in terms of, is this a multi-layer perceptron? Is it a convolutional neural network, kind of a standard one, or whether it is a ResNet architecture from computer vision. And we will see that basically graphs that have certain structures perform better than networks or neural networks that don't have those kinds of structures. And then what is interesting is that we can even take biological neural networks, meaning the real networks of brain of animals, and actually find correspondences between our artificial neural networks and real neural networks. And I'll show some results about that as well. So first, I need to tell you about the novel graph representation of neural networks that we call relational graphs. The way this works is that basically the way we think of neural networks is we think of them today as what we call computational graphs, or these direct acyclic graphs, where basically we have these layers of neurons, and then layers in neurons in one layer kind of talk to layers to neurons in the next layer. And perhaps you have skip connections and things like that, but essentially we think of this as this kind of templatized layer by layer graphs, right? So if I have a multi-layer perceptron model here on the left, just kind of schematically, then the computational graph is here in the middle in black, where the circles are neurons and edges represent connections, how one neuron sends its messages to other neurons, and then each neuron collects messages from the neurons on the top layer and computes its own activation, right? And in particular, in this work, we will be focusing on studying a single layer of this multi-layer neural network, where basically what we have is a set of neurons and a set of connections between the neurons, and these connections say how one neuron is kind of pushing or sharing information with other neurons. So, and when people try to study the performance of neural networks and their architecture on the underlying predictive performance, they generally look at these computation graphs, basically layer by layer graphs. What is, for example, interesting to see is that there has been some work where basically they show that even if you create this kind of random layer by layer networks, what is called randwire, you can still get quite competitive performance against this type of neural networks that humans or scientists can design. But there are many important limitations of this computational layer by layer graph representation of neural networks. First is that this is a very kind of templatized and rigid structure. It only allows for directed acyclic graphs, and there is a lot of kind of this copying of the same template of these bipartite structures between individual layers. And so that's one kind of limitation. And the other limitation is that it is kind of disconnected from the underlying neuroscience, where brain networks have much more flexible structures. They allow for bidirectional information exchange and so on. So we want to come up with new representation of neural networks that will then allow us to study their structures. So this is what we want. We want a better graphical representation of the neural network architecture. And we develop it and we call it what we think about is that we think of neurons in two layers. And the way we think of this kind of communication across one layer of the neural network is that the connections in the layer basically say how a given neuron sends its activation to other neurons. So here, for example, neuron 1 sends activations to 1, 2, and 4 in the next layer. And then, of course, at the next layer, every node aggregates these activations coming in and then decides whether it wants to activate itself or not. And the way we are going to represent a single layer of the neural network is we are going to represent it with a relational graph, where basically what edges here will mean is that a node is connected to another node if the node in one layer sends a message in the other layer. So for example, node 1 sends messages to 1, 2, and 4. So node 1 is connected to itself because it sends a message to itself. It sends a message to 2 and sends a message to 4. But it's not connected to 3 because node 1 is not sending a message here to node 3. So here we are now making assumption that between the two layers we have the same number of neurons, and now we can basically encode this bipartite structure by basically folding it to get this type of graph. Here I'm thinking of this as an undirected graph. You could imagine having this as directed graphs as well. But just for the simplicity of representation, I will think of this as undirected graphs, these relational graphs, right? And basically all I need to do, if I want to have this computational graph and I want to find its relational representation, I need to fold this computational graph by basically computing AA transpose in some sense, right? So that's what I get. And I think the important thing is that what we do here is essentially we can see one layer of computation as one step of some kind of message exchange, right? Where one neuron exchanges messages, its activation with other neurons. And this is what we encode in this picture here. So basically, the way we do this is that in the relational graph, we create one relational graph per layer. Neurons of the layer are nodes in the relational graph, and edges specify the connectivity between in the bipartite graph, specifying one layer of neural network computation. So this is now, and basically one layer computation is reduces to the computation by basically nodes sending messages to each other and kind of updating its state. And now if we want to generalize this to multiple layers, we can basically do multiple rounds of message exchange over this same relational graph, right? And this is essentially the idea where we can basically think of message exchange as different layers of computation, right? Where basically nodes talk to each other and exchange activations. And this is very interesting because it has relations to how we think of graph neural networks, which are basically convolutional neural networks or neural networks generalized to graph data. So this is the way we represent, right? So given any kind of neural network, we can represent it using its relational graph structure, where rather than thinking of computation as a way of, in some sense, layer by layer message passing, we are thinking of it as message passing between a set of nodes, and we think of this as multiple rounds of this message passing. So this is the representation, right? So just to give you an example, right? If I have a neural network, one layer of the neural network that looks like this, then a relational graph representation is depicted here, again, as an undirected graph, which means that one sends a message to two and two sends a message to one. So 1 and 2 are connected, but 3 and 4 are not connected to anyone. So that's one example. For example, just a pass-through layer would simply be a set of nodes with self loops, because every node just kind of passes information to itself in the next layer. So that's kind of one round of message exchange on top of the relational graph. So what are some benefits of this approach? The benefits are that there is a deterministic one-to-one mapping between the computational graph and the relational graphs. What this buys us is now that relational graphs are arbitrary graph structures. So there is no restriction on the graph structure as it is in the computational graph, where these graphs have to be bipartite and DAGs. And what is interesting is that we can now also take real-world neural networks and kind of interpret them as neural network architectures with multiple layers of or multiple rounds of message exchange to basically get a deep neural network. So these are the benefits. Now, what I want to do next is show you that this simple approach allows us to represent many different neural network structures. And there are 4 different components that one needs to specify when, let's say, defining a neural network, or through the computational graph, or through the relational graph that we propose. So first is, for every node, for every neuron, we have to define what are the features, what is the what is the message that the neuron takes. So for example, in a classical perceptron, each node has a unidimensional feature. It's basically the magnitude of the signal. Then we need a way to we need a message function that basically says how is the message transformed. In multi-layer in a perceptron, it's simply a weight, right? It's a feature multiplied by weight. Then we need to decide how these activations from multiple neurons are aggregated after they have been multiplied with the weight. We sum them together and we pass them through a nonlinearity. And that's what is a perceptron. For example, if we want to have a variable width perceptron, then basically what we can change is we keep the multiplication with the weight the same, we keep the aggregation function the same, but what we can change is we can change the dimensionality of each neuron, its feature dimensionality that can vary, so that we can kind of change the width of the network. In convolutional neural networks, the features are tensors of multiple channels of data, right? So we have multiple channels in the image. We have this kind of convolutional operator, and that's basically a little matrix, and we have multiple of them because we have multiple channels. So it's a little window of an image. And then, a message function is, let's say, a 3x3 convolution. Aggregation function is, again, a summation. And, the depth is basically corresponds to the number of rounds of message passing. So in our case, ResNet 34 would be 34 rounds of message passing, including the residual connections. But, we can do ResNet 50 by having 50 rounds of this message passing on top of the relational graph. And I can show you other examples of other kind of classical neural network architectures that can nicely be represented in this new representation. So with this kind of explaining how we have a new representation of neural networks and how this representation works, I want to now give you some empirical observations when we study neural networks through the lens of their relational graph representation. So our methodology will be the following. This is something, as you will see, that requires a lot of computational resources. And this only allowed us basically to do this through collaboration with Facebook, who has practically an infinite amount of GPUs, because this will require a lot of GPU training, as you will see. So basically, the idea is that we will generate many different relational graphs, right? We will generate general graphs. We'll use various kinds of graph generator models to generate a relational graph. We will then take this relational graph and kind of generate its corresponding computational graph. Now that we have the corresponding computational graph, so basically the neural network architecture, we are going to train this architecture and measure its predictive performance on the holdout test set. And then the question is there a connection between the structure of this relational graph and the performance of the underlying neural network that we have trained that has this relational graph representation, right? So first question is, how are we going to characterize relational graphs? And the way we are going to characterize relational graphs is that we are going to measure two properties that are kind of classical measures of graph structure in network science. One is called the average path length, which is the average shortest path difference between any pairs of nodes in a graph. And the second one is clustering coefficient, which is a measure of the degree to which nodes in a graph tend to cluster together. So it's basically a measure of how many triangles or how many triples of nodes in the graph are connected with each other, right? So here is a network that has high clustering, and here is a network that has a very low clustering. And looking again at my example in the middle, this should also have clustering 0 because no triple of nodes is connected. There is no clique of size 3. So I think that's an error here. So this is how we are going to characterize relational graphs. So now the question is, how can we cover the space of all relational graphs, which is in some sense, how can we generate in some sense all possible undirected graphs on a given number of nodes? And what I try to show you here is this is the space of clustering coefficient and shortest path length. And here with different colors, I show you different graph generators where every dot is a different graph. So for example, if you do small world graphs, so what's Strogat's graph generator, and you play with the parameters in that graph generator, you get these red graphs as characterized by clustering coefficient and every shortest path length. If you create a fully connected graph, a completely connected graph, you are this X, black X point here, you have clustering coefficient of 1 and shortest path length of 1. If you are creating Poisson random graphs, so Erdős-Rényi graph generator, and you change the connection probability P, you get these blue graphs here. For example, if you generate ring graphs, here are the ring graphs. If you generate, Barabasi-Albert scale-free graphs, these graphs are here in yellow. And of course, you see that we are not able to cover this space. That there is quite a bit of white space here, where we basically are not able to generate graphs with a given clustering coefficient and every shortest path length. So we have extended the small world graph generator into something we call WS Flex, and it's described in the paper, that basically allows us to cover this space of graphs characterized by every shortest path length and clustering coefficient. So every dot here is a different graph, and we kind of generate them all. And now that we have generated a given relational graph, what we will do is we are going to take this relational graph and translate it into the neural network architecture, and then train that neural network architecture. And of course, one point is that we can take this space of graphs characterized by shortest path length and clustering coefficient, and we can sample it more or less densely, or with more or less fine grid. So here is another sampling of this space with a bit coarser resolution. And again, here I show you, for example, a complete graph. This would be a fully connected layer. Is this point here? This is a different graph. Something up here is almost like a ring graph, where basically neurons only share information with its immediate left and immediate right neighbor, and so on. So now one important detail here is that the number of nodes, the number of other neurons a given neuron communicates with, is directly related to the amount of computation we have to do. And because we would like to compare different architectures, we need to condition on the amount of computational budget we have. So the way we are doing this is basically noticing that the more edges the relational graph has, the more computation we have to do, because the more messages we have to pass and sum up together. So the number of floating point operations is directly related to the number of edges in the graph. So the graph on the left uses less computation than the graph on the right. And kind of the idea is, because the graph on the right, the graph B, uses more computation, it will likely have higher predictive performance. So what we are doing to equalize computation between different graph structures is that we play with the dimensionality of nodes. And this basically allows us to equalize the amount of computation in one graph versus in the other graph. So in some sense, we can make one architecture more dimensional, to use more dimensions, and this allows us to compare two different architectures with the same amount of computation, but having different architectures. And more details about this are in the paper, but this is something that was very important to us, so that we really compare architectures and not the computational power of different models. So now what is our experimental setup? As I said, we are going to generate many, hundreds or thousands of these different relational graphs. We are going to translate relational graphs into neural networks. We are then going to take a data set and train each of these neural networks on our data set. We are going to train this neural network, each neural network, 5 different times, because it's a non-convex optimization problem. So we wanna also estimate, we wanna get a more robust estimate. So we will train it 5 different times. and then we will plot its predictive performance as a dot of different color in this space of all architectures, right? So now you imagine that this is a lot of really a lot of computation, because I can have a few hundred graphs here. Then for each of these graphs, I need to train the model 5 times, and then for every such path, I get one dot in this plot, where in this case the color corresponds to the predictive performance. Here, top 1 error on an image classification data set called CFAR10. And CFAR10 is small, but if you have now ImageNet that is 1 million images, and even training one model takes a lot of time, then training hundreds or thousands of models takes a lot of time. So we are going to do this on several different data sets, as well as different architectures. We are going to use multi-layer perceptrons on CFAR10, where we are going to train over 4,000 different graphs, different neural network architectures 5 times. So that's 20,000 different models. Then we will use convolutional neural network, ResNet families, and EfficientNet families on ImageNet, where we will be training 52 different architectures and average over 5 different experiments. Oh, sorry, 3 different experiments or 3 different seeds. And we will control computational budgets so that computational budgets in all the cases are the same. So let me now walk you through the findings. The first finding is that we find that neural networks that perform best kind of have consistent architecture, have consistent structure in their relational graph representation. So as I said before, what we will be looking at are these average path length versus clustering coefficient plots. Every dot here is a different model. The baseline, what people like to do today, is the model here at is the dot at coordinates 1, 1, because this is a fully connected layer. For example, if you do that today, it will give you an error of 33.34. And the best architecture with the same computational complexity is this X here that has far better predictive performance. Again, this for people who are with computer vision background, this is a very big performance improvement, even though it kind of absolutely seems small, but this is very significant for a 5-layer multi-layer perceptron. And then what we are going to do is basically we are going to ask, what is the region of the models in this CL space that perform significantly better than the baseline model, which is a fully connected model that is here at the bottom right. And we are going to show this area with a red square, right? And we will call this a sweet spot because all these models perform better than the baseline architecture that kind of is a standard today. And here I show you for different data sets and different architectures, multi-layer perceptron on CFAR10, convolutional neural networks on ImageNet, ResNet on ImageNet, a different sub-architecture of ResNet, different depth of ResNet, and EfficientNet on ImageNet. And I show you kind of the size of the space where the models are better. And what is important to know is that all the dots here are models with the same computational complexity, but of course a 5-layer MLP has much less computational complexity than a ResNet 34, and the ResNet 34 has smaller computational complexity than the ResNet 50 because 50 has 50 layers. But again, you can see that even though here, for example, on the left we have about, I don't know, 3 million floating point operations, and on the right we have 3.6 billion. The best architectures are quite consistent, somewhere here in the middle of this clustering coefficient shortest path length space. So the first thing is that best architectures are in the consistent region of the space. The second thing is that what we find, and it's also interesting, is that neural network performance is approximately smooth function of these graph measures. I just show you right here here's again our 4,000 different graphs, and I will show you projections of kind of slices of this space on one of the two axes. Here is the projection of this area here on the shortest path length, and here is the projection on the clustering coefficient. And again, there is noise because, of course, this is real data, non-convex optimization problem and all that. But again, you can see that there seems to be some monotonicity in this plot. This is for 4,000 graph. This is now an ImageNet with a smaller number of graphs, and here are the plots, the fits to the dots. Again, there is noise, but you can see this kind of approximate smoothness in this space. So that's another interesting observation. Third observation I want to mention is that this sweet spot, right? So basically, the best architecture can be quite quickly identified. And the way we do this is we say, what happens if you take your space of graphs and you sample it very finely, and then you say what is the best architecture I find over, let's say, 4,000 graphs, and how good is the architecture that I find if I sample this space in a more coarse way. And here is kind of how many different architectures do we consider. And here I show you, the picture with almost 4,000 different architectures we consider, and a picture with only 52 architectures considered. And of course, 52 is about 2 orders of magnitude less than 4,000. But again, you see that we have quite consistent results, perhaps a bit more noisy, but again, the same region, the same set of parameter space wins as it did in the first case. So it means we don't need to sample this space very densely, or we can kind of sample it adaptively. And then the second thing is, how many iterations of training, how many epochs of training do we need before we can identify whether a given architecture is good or not? And here on the right, we train for 100 epochs, and here on the left, we only train for 3 epochs. And we basically see that networks that perform well after 100 epochs are the same as the ones that perform well after just 3 epochs of training. So we can identify good networks very, very quickly after just a few rounds of training. Here I show you, these are training rounds versus Pearson correlation between the performance after K rounds versus performance after more than 100 rounds of training. And you see we need about 3 rounds to reach, to identify well-performing networks. And then the last thing I want to talk is about interesting and intriguing connections to neuroscience. Here, the first thing we find is that if we measure the clustering coefficient and shortest path length of real neural networks, so basically cortex of different mammals, we find that they have quite similar graph structures. So for example, cortex of a cat has the average shortest path length of 1.8 and clustering coefficient of about 0.55. And macaque, basically a monkey, has shortest path length that's shorter and clustering coefficient that's a bit smaller. And the entire cortex of macaque, this was just visual. The whole cortex has, average shortest path length that's about 2.4 and clustering of about 0.46. If we find what is the range of neural network architectures that we find that have good predictive performance, we see that the shortest path length is between 2 and 2.3, and clustering is between 4 and let's say 0.6. We see that the macaque whole cortex is quite close in its structure to the sweet spot we identify, as well as to the best, let's say, 5-layer multi-layer perceptron, its clustering coefficient, and the shortest path length, right? So kind of it is interesting that this connection about the relationship or the similarity of metrics is quite interesting. Another thing we can do is that we can take each of these networks, both artificial ones and real ones, and we can train them on an image recognition task on CIFAR 10. And here is the predictive performance of these networks, right? As I said, the complete graph will give you about 0.33. The cat cortex is just network is just a bit better than the complete graph, and you know the macaque network is better than the cat's cortex. And what is interesting is that these networks perform better than fully connected layer, and that their performance kind of gets closer and closer to the best architecture we identify. So this is kind of the second point, is that as kind of these organisms get more complex, their predictive performance when trained on CIFAR 10 also is increasing. These are the three observations that are interesting from the neuroscience point of view. So to conclude, right, like in this work, I basically proposed to study the structure of neural networks using the tools of network science. And rather than studying the conventional computational architecture, the computational graph structure of the neural network, we have proposed this new way of representing neural networks as graphs called relational graphs, and showed that if we study them as relational graphs, we observe many interesting patterns. This is our work. Here are my co-authors. Here is the link to the archive where you can find the paper. And we also have released, I think, the data and the models, so you can play with this and analyze the data further to make additional observations. And then last thing I want to say in the last 5 minutes of my talk is to let you know about an effort we have started at Stanford with an international group of collaborators. So basically, we have a project called Open Graph Benchmark, which is an ongoing effort for large-scale realistic benchmark for machine learning with graphs. And Open Graph Benchmark is a set of benchmark data sets that allow us to benchmark different approaches, algorithms on different tasks of graph learning. So first important thing is that these data sets are ready to use for different tasks. We have node classification tasks, link prediction tasks, and graph classification tasks. We provide both the splitting of these data sets onto the training, evaluation, and test data sets. So all that is standardized. And we also provide a code base to load, construct, and represent graphs. And we are supporting popular deep learning frameworks like the Deep Graph library from Amazon and PyTorch geometric that is built on top of PyTorch coming from Facebook. And we also provide a common code base to measure, to evaluate performance metrics so that comparisons are fast and fair between different models. And one important thing is we put a lot of effort into coming up with data splits that really try to focus on generalization of the model. So rather than doing this kind of cross-validation random splits, for example, we would do splits based on time, where you learn on some number of years, and then you have to predict the state in the future years. Or, for example, for molecule classification, we would do what chemists call scaffold splitting, so that it is the focus is how do you generalize to novel molecule structure rather than how do you memorize the molecular structures you have seen during training. So the goal is that we provide code so that a person who's interested in this graph-based learning can only provide the model, and the rest gets done in a standard way, so that the performance across different tasks, across different data sets, can be accurately tracked, so that we can make more progress as a community in this area. We have 3 different dimensions along which these data sets vary. As I said, we have 3 different tasks: node, link, and graph. Node classification, link prediction, graph classification. We have different sizes, what we call small, which is something that fits into memory of a single GPU, to medium, to large, where more sampling-based approaches and scalability becomes more of an issue. We think of this as interesting challenges that will push us forward. And then we deliberately get the data sets from many different domains, like chemistry, biology, social information networks, as well as heterogeneous knowledge graphs. If you are interested about using these data sets, they are available at ogb.stanford.edu. If you'd like to send us email, you can email us at ogb@cs.stanford.edu. We have a core development team at Stanford, Microsoft, as well as in Europe, and international steering committee that is basically providing guidance and feedback on the project, so we can really create a resource that is useful for the entire graph-based learning community. So with this, I'm done, and very happy to take questions.
Great talk. Any questions for Yuri? Yeah, let me start with one question that I have. So, I'm wondering about this computational budget aspect that you highlighted that this is very important. So, I have a question related to this. So, naively, I would expect that kind of a fully connected graph encompasses everything. So, in particular, I can just in a fully connected graph just set some of the links to 0 and then get back to different graphs. However, because of this computational budget adjustment, the dimensionality of my nodes will be smaller. So I was wondering, does it make sense to set this computational budget not a priori, but after a couple of, let's say, burn-in time, a couple of epochs of training, when the neural network have a possibility to set some of the weights in the graph to 0, and thus kind of reduce the network automatically, and only after that do this kind of computational budget adjustment. So the suggestion is, the question is, do you expect that in this case the fully connected network will win everything, or not?
So perhaps a few things to say. I think the first thing to say is you can think, of course, a fully connected layer can set a lot of weights to 0 and then mimic any kind of relational graph structure. But in our setting, the question then is, do you want to have one dense layer, or do you want to have kind of multiple sparse layers, right? And this is in some sense the trade-off that we are exploring. What we are doing here is that we are essentially, by selecting the relational graph, in some sense, we are presetting certain weights in the layer to be 0, and we don't learn over them. Of course, one thing that is also important is that today we like to make dense layers because from the GPU perspective, it is just a matrix vector product, and it doesn't, even if that matrix is sparse, it doesn't gain anything based on our current computational architectures, right? So, but in the future, if we are able to compute over sparse layers efficiently, this might be more useful. Right, so that's, I think, another kind of practical consideration, is that these models are actually kind of slow in practice because the GPU has to do the same amount of work as it would in a fully connected layer, because the way the kind of the data processing computational pipelines are set in these graphical processors.
Okay, thank you.
Yeah, good question. Thank you.
Any other questions? I don't see any for now, so maybe we can push to our discussion to the breakout room and then continue there.